Hi, today I'm gonna start to talk about internal forces. When we're dealing uh, with the structure and want to design any kind of structure, mostly we need the internal forces in order to find the correct shape and design and all the things that we need for designing the structure elements. Uh, Previously, we looked at the truss and a little bit on the frames, and we'll look at how those internal forces um, can be calculated. Today, we're going to look deeper in how to find the internal forces in any type of structure. So, to start with, we assume we have a beam that is um, fixed at one end, and there is a force on the other end. So, assume we have a beam look like this, and there's a fixed point here is a point A. And then we have a kind of forces, just one force, assume there is one force applied in one end. Um, and then we'll call this point as point B. And then we want to see what's happening at point, if this is this section here, if this point here is point C, we want to find out under this condition how much is going to be the internal force at the point C. So before doing that, we will go ahead and I will go ahead and draw the free body diagram of this beam. So if I go ahead and draw the free body diagram of that, we will have the beam itself, and then we will have the external forces, all the external forces or moment we have, and then we will have all the reaction of the support, for example, here. So we will have at that point A, we'll have the AX, no, we'll have the AY, um, so at point A we have AX, we have AY, and we have the moment point A. So we have these are as the external as a reaction. This is the external force, and then we want to know if there's a point C here, how much the internal force is at that point C. So what we will do generally is just that assume I will go ahead and I will cut through. In other words, assume I cut this at point C. So I divide these beams into two beams. So is one of them is going to be from point A, if it's here, to point C, and the another one is going to be from the C to point B, and I'm going to draw them to see what we will have. So we have two sections. If I assume I cut through the C, we would have the section AC, so it's going to be the section AC, and so it's the A, and this is the C, and then we will have the section CB. So this is going to be section CB. And now we'll put external forces in each section. So here we'll have the only external forces we have is the F. So we have the F here, and we have the reaction of the supports here. So we have AX here. So we have so AX is here, AY, and the M at point A. Now that we cut through this section, before we cut through, whatever force we have here is the internal force, and we don't care about it much. That's the internal force. But as soon as we cut it and we split it in two, then those internal force become external forces for each section. I want to look at what forces do we have. So the very first force we have uh, would be the forces that is going to be along the members. So assume that we have this one. So we will have forces along the member. And these forces, whatever is applied on the left side, is going to be applied the same on the right side. And these forces, we usually show it with the N at C. That's going to be N at C. And this is called the normal force. So it's called the normal force. And in other words, it's just in normal to the cross section, or is aligned with the section itself, aligned in the member itself. It's either compression. Here I draw them as a tension, but it can be tension or it can be compression. Either way. So we will calculate, and then we know that when we do the calculation. The second type of the forces we will have here would be the forces that is let's say like this. So we would have the forces that are normal to this normal section, or in other words, is the parallel to cross section. So these forces would be, for example, like this or like that here, and these forces we will call them V. So it's short by VC. It's going to show what VC, and generally this one is called a shear force. So if you look at that shear force actually wants to cut the section. This shear force wants to cut the section. So on the normal force want to compress it or pull it apart, but the shear force wants to cut it through. And remember, if you have the shear force pointing downward here, we're going to have the opposite of that on the other side. So it's going up, downward, it's going to be upward. And the third one that we have, and we will work with that, is the moment. So we have two moments here, and we call it the MC, the moment at C. As basically these are called bending moment, and what they tend to do is that they tend to bend this beam. So they want to bend it either upward or downward. It's like that we have the ruler and we just bend that ruler. Those bending moment try to bend it either upward or downward. So if we cut the section as we have here, we will have these two forces, one moment in each section. So we have one is in the normal of the section, one is the one to cut the section, is the shear, and then one to bend the section. So we have normal, shear, and bend this section. So these are the mainly forces we have in 2D section. When it comes to the 3D, we will have a little bit more detail of that. We have more forces if it comes to 3D. So let me a bit up. So in 3D, assume I'm going to draw the 3D beam. So assume that beam we had, but this time is going to be in 3D. So I'm not going to put any forces on that. So assume we have the beam in 3D, something like that. And there are some forces on that and some support on that. For example, assume we have some forces applying on that beam, and then there are some moment applying on that. We don't know, and then it's also is supported by the wall at this section, so it's completely fixed into the wall. So assume this is the 3D. It's the very same thing that we had before for the 2D, but this time it's 3D. So we have A, B, and then this is the cross section C. So this time we want to see what's happening at this cross section C, but this time is a 3D. The same as before, I will go ahead and cut this again through that section. So I will cut this here, and I will show what's happening. This time I will only show the AC section, so and also only the section view to show what's happening. So assume this is what I'm gonna get in case of that cross section. So this is the point A and this is the point C, and then I'm gonna put the axis there. So I assume I have my axis there. So I have the x-axis going this way, I have my y-axis going this way, and then I have the z-axis going up. And this is the z-axis. Now I want to show you about what forces do I have here. So I would have one forces along each of the x, y, and z directions. So I would put them one, let's say for example, assume, so I have one along the y-axis, so I would call it ny, and I have let's say two of them along the one of them along the x, so it's the nx, and there's another one here nz. So I have these one going along the x, y, and z axis, and then I would have three moments about each of the axis as well. So if I go ahead and I would have one moment about the x-axis, so I would call this mx. I would have one moment going about the z-axis, so it's the mz, and have one moment going about the let's say y-axis, and let's show it with for example so we have also one going about the so let me show it with another color so it distinguish from the other two. So we have another one going about the y-axis. Now if you look at here about the forces that we have, if I go here and look at this one is the normal forces, so is normal to the cross section. So the n along the y1 is the normal force, so it's the normal force, and going just it's perpendicular to the normal to the cross section. The nx and nz, if you look at the nx and nz, both nx and nz, they want to cut the cross section. Both of them, assume if we have those forces, they want to cut through the cross section. So both nx and nz are shear forces. So among these three, one of them is normal force, the other two are shears. Now if we look at the mx and mz, we will see that the mx and mz, they both want to bend this section. So in this one, mx wants to bend it about the x, and mz want to bend it about the z. So mx is a bending moment, similarly mx is bending moment. But if you look at the my doesn't want to bend it, it want to twist that section. So it's one, if the section is not connected to anywhere, it's one rotate this whole element, so it's gonna twist it, and because of that it's called a torsion moment. Basically, it wants to twist that section, so it's going to be the torsion moment. So these are how the internal forces would be in the 3D. So we have three forces and three moments. One force is normal, two forces are try to cutting or basically are shear. Uh, they're cutting the cross section, and two moment are bending the element, and one moment wants to rotate or twist that element. So it's how it would be in 3D format. Also, when we want to work with this, so let's go back to 2D. One thing that we have to make sure is that there is a conventional way of considering the positive direction for the moment. So if I draw again the 2D beam we had, so I have the beam here connected to the wall at point A. So this is the beam, and this is the point B, and there's a point C that we want to see what's happening there, and then we had some external forces applying on that point as B at F. And if we want to see what's happening at point C, we said we will cut it at point C and we split it into two and we draw that. So when we actually do that, we draw the section AC. So that's going to be the section AC, and then we have the section CB, and then we put the external forces on that. So that's the only external forces we have is the F, and then we have the reaction of the support. So we'll have the AX, AY, and the M at A, and then we will want to put the internal forces to see how they look like. So when it comes to the internal forces, the normal forces considered positive if they are in tension format. So if this is the N at C, this is the positive force, so it's a tension, and the same, they are considered positive if it's at the as the tension. So it is a standard. So always when they say the normal force is positive, that means that the section is in tension. The same, not the same for the shear forces. If we will go ahead and look at the shear forces is going to be positive for this left hand side if it goes downward, and it's considered positive for the right hand side if it's going upward. So this is the positive for the shear stress, so it's going downward here and going upward here. And for bending moment, when we call it as the bending moment is the positive or bending moment is negative, it would be if we have it like that. So if we have the M is like that, they are considered as positive. So these are the conventional positive direction for the normal forces, for the shear forces, and for the bending moment. So whenever they said they are positive, it means that they're following these direction or senses. If they are negative, it means that the direction is against this conventional direction. And this is what we use when we want to analyze or we do the example or we calculate these forces. These are, make sure that you always draw them in a positive format and then do the calculation. So if it comes positive, everyone knows that you mean this direction. If it comes negative, again, everyone means that they are opposite of this direction. Now let's look at an example. Assume we have a beam here and it's going from section A to B, from support A to B, and the pin support and the roller support at B, pin support at A. It has a single force 50 Newton apply here, and then it has a distributed load 100 Newton per meter apply here, and then want to know what's the cross section, what's the internal force at C. Remember, every time that we have the problem that we ask us if there is a what's the internal force cross section. First, look at if I cut it through and split it in two. Do I need the reaction in for my analysis or not? Sometimes you may not need them. Sometimes, for example, you may split it into, and one section of that does not have any um, uh, let's say support reaction. For example, I draw very quickly here example. Assume I have a beam here uh, like that, and then there's a force here, and there's a, for example, A, B, and then there's a point C here. I want to find across the reaction there. If I go ahead and cut it through from point C, and I look at this the section CB, there's no reaction. So if I draw the CB here, there's no reaction of the support. All the support reaction are going to be at A. So I don't actually need to calculate any reaction here. I can go ahead, right ahead, split it into, pull out the CB section and start to analyzing this section. I said, okay, this is my normal force, this is my N, this is the V, and this is the M. So I can go ahead directly start to analyze this section without calculating the reaction. But if you look at here, if I cut through this section and split it into two, either I choose the left side or right side, I'm gonna end up having the reaction in that section. So if I choose the left side, I would have the reaction at A. If I choose the right side, I would have the reaction at B. So there's no way that I can cut this in two and analyze it without knowing the reaction. Here it's possible to do that, here it's not. So first check if you can do the analyzing without calculating the reaction. It saves you some time. It's not gonna hurt you to find the reaction. You may not gonna need it, but so you can do it without doing those reactions. But if you need the reaction, so as I said, always first go ahead and consider the entire body and find the reaction. Here is the case. If I split it into, there's no way that I can do the calculation. Either I consider the AC or I consider the CB. I need the reaction in both of them. So there's one thing that I need to do. So I'm gonna clean this part and go back to our example. The other point I want to make that uh, when we are working with this, do not change the force until after you split the section and isolate the section you want to work with. So do not replace these forces um, for your section view, for your section analysis. When try to keep it the way it is, and after you did cross section it, after that you replace the forces with the resultant one. So here I will go ahead and I will consider the entire body as it is, and I will find the reaction. So I would go ahead and say if I had the entire body, let's say that I would have here I have AY and I have AX, and then here I have BY. So if I consider the whole body, so I would go say that if I consider the whole AB section, and I write the equilibrium equation there. So the first thing I can go ahead and write is I can say sigma of x is 0. Therefore, if I look at here, the only forces I have in the x-axis is ax. I have no other force in the x direction, so it's going to be 0. Now if I write a sigma ay is 0, I would not get anything out of that because of both these, I have two unknown. So I have to write the, I have to write a moment about point A or point B. I can choose any of them to write. For example, I would do calculate a moment about point A because both AX and AY go through the point A. They don't have any moment. So the forces that have the moment is this one, is the resultant of this one, and the BY. So if I go ahead and write a sigma M about point A is 0, and as always we consider the counterclockwise positive. Then the forces I would have here is that, now let's put that resultant force there so we can use it. The resultant force for this is going to be a force is going to be applied right at the center of this rectangle, and the magnitude of that would be the area of that triangle, which is 100 times 2. So it's the 100 times, so the height is 100, the length is 2, so it's the magnitude of that force, and it's going to be right at the center of that rectangle. So if I draw the free body diagram very quick here, a simple free body diagram, that's what I have here. So I would have AX, I would have AY, I would have 50 Newton here, I would have 200 Newton here, and there I would have BY here. And if I write the moment about point A, then AX and AY doesn't have any moment about point A. It's going to be the 50 here, so it's going to be the 50 and times this distance, which is going to be 1. So times 1, and it's going to rotate it like that. So it's going to rotate this section as like this. So it's going to be rotated clockwise. So it's going to be negative. So we put a negative sign here. And then we have the 200. So it's going to be plus. It's going to be 200 the force, and the distance from 200 to A is from here to there. So it's going to be 1, 1, 1, and it's going to be half of this is 1, so it's going to be 4. So it's times 4, and again the 200 about point A is going to rotate this like that. It's going to be clockwise again, so it's going to be negative. And so it's going to be negative. And then we have the BY, which is going to be plus. It's going to be BY and times the normal distance between B and A, which is going to be from B to A, which is 5. And it's going to rotate it like that about point A. It's going to rotate it like that, so it's counterclockwise, so it's positive. And it's going to be 0. So therefore, if we do the calculation, the BY would be 117 Newton. And then if you write the sigma Fy is 0, then what we have is the Ay minus 50 minus 200 plus By is 0, and therefore that Ay would comes out at 80 Newton. So this is what we are gonna have here. Now I would go ahead, okay, let me clean that free body diagram. So now I would go ahead and start drawing the So I will go ahead and cross section it at there. So we want to know the internal force, so we have to go ahead and um, cross section it there. So remember, when we do the cross sectioning, we are not using the resultant force. We keep the force in their initial condition until after we do the cross section, and then we after we section them into, we will replace them. So I will draw them. So it's going to be the AC here. So it's going to be the section AC, and so if I consider these as point A, that's the A, and this is the C, and then we have the section CB here. So it's the section C and this is section B. And then we put the internal forces, and I said put the external forces, put them exactly the way they are. Don't put the resultant forces, because sometimes the cross section might go through the distributed load and split the distributed load between two sections. So try to keep them the way they are before doing that. So you will have the 50 Newton there. So it's a 50 Newton applying there. And then we have this distributed load also applying at this section. So it's 100 Newton per meter. And then we have the external forces. So we have the AX, AY, and AZ. So we have AX and AY. So we have the AX, we have the AY here, and then we have the BY here. And then we have the internal forces. So we have the and remember, we draw them as a normal direction. So we have the N, C here. Then we have the shear forces. So this is going to be the normal direction, or the positive direction. So it's going to be the V. It's going to be the V, and then we have the moment at C. So it's M at C. It's going to be M at C. Also, those are at C. So now we have them. We cut it through point C, and we put all the internal forces there. Now we have a choice to go consider the section AC and analyze that section to find these forces, or we can go ahead and look at the section CB. So in either way, we can go. If we consider the section AC, we'll write 3 equilibrium equation for section AC, or we can go ahead and build section BC and do write the section BC3 equilibrium equation there. We can do it with either of them. Sometimes we need to do that for both sections. So if I want to do that, so either we go ahead with section AC, and then we will write the 3 equilibrium equation there. So we write the sigma fx 0, sigma fy 0, and sigma m 0. Or we go ahead for section CB, and we write the 3 equilibrium equation again. We can write sigma fx 0, sigma fy 0, or sigma m 0 for either of these two. So if we can have them either for this one, so we can write this section for this half, or we can write it for this half. And as I said, sometimes we may need to write it for both sections. We may need to write the 3 equilibrium equation for AC, or we may need to write the 3 equation for CB. So depend on how many unknown we have. Here we have only 3 unknowns, so we can only choose one of these two sides and write it. If we have more than 3 unknown, then we would have to write the equilibrium equation for both sections. So assume we had 6 unknown, or in that case we will have to use all of them. So I will choose the left side, so I will write the equilibrium equation for the left side. So I'm gonna draw the line here. So I will write the equilibrium equation for the BC for the AC section. And if I write the equilibrium equation for the AC, I would start with the sigma fx is 0. So if I write the sigma fx is 0, I have ax plus nc is 0, and I know the ax is, I know already ax is 0, so I know ax is 0. Therefore the nc would be 0. So there's no normal forces here. Also I can go ahead and write sigma fy is 0. So if I write the sigma fy is 0, then if you look at this section, I have ay, the positive direction, I have negative 50, and then I have negative vc is 0. And ay I already from here is, I know it's 80, so I know it is ay is 80. And if I substitute in that, the vc would be come out at 30 Newton positive. And then I need to find the MC. When we want to find the MC, the easiest way of doing that is just go ahead and write the moment about the section, because when you write the moment about the section, those normal force and the shear force does not have a moment about that section, because both of them pass through that section, so they don't create any moment about that section. This, most of the time, I said always it's easier to do that. So if I write moment about point C, then and consider the counterclockwise positive. So again, this NC doesn't have any moment because it goes through point C. The VC doesn't have any moment because it goes through point C. The AX is also going through point C. It doesn't have any moment. So only the AY, the 50, and the MC would be considered. So I will start with the AY. So I have the AY and times the normal distance between the AY and C, which is going to be from here to here, is going to be 2 meters times 2, and it's about point C. AY is want to rotate like that, about point C is rotate like that, so it's going to be clockwise, so it's going to be negative. And then we have the 50 Newton, and the normal distance between 50 and point C, the 50 and point C is just 1, so it's going to be 1, and it's going to rotate that section about point C. About point C, it's going to rotate it, the 50 Newton is going to rotate it like that, so it's going to be counterclockwise, so it's positive, so it's going to be positive here. And then we have the MC itself, which is rotating counterclockwise, and it's going to be positive as well, so it's going to be MC, it's going to be 0, and therefore if we, and we know that AY is again is 80, so if we substitute everything there, so we have the AY here, so the M sub C would comes out as 110 Newton per meter. We could have done the same calculation using the section CB. If we use the section CB instead of AC and write these three equations, we would get the same result as we have here. So we don't need the section AC is easier to do that. So always choose the section that is easier, unless you need to choose both sections. Sometimes you need to choose both sections and write all the equilibrium for both sections. You need to write 3 here and 3 here, and total 6 equilibrium. Otherwise, choose the section that is easier and write the equilibrium equation for that section, and then you will find you can find all the internal forces and moment for that section.